right, yeah. So Sukdeep is going to start us off telling us about fundamental plane of boss galaxies. Okay,
Yeah, so I was supposed to talk about covariances, but then I was hiding away yesterday and I got caught. So I think it was a good excuse for me to instead talk about like this recent work we have been doing to measure the fundamental plane of boss galaxies and then estimate the impact of intrinsic alignments on the redshift space distortion measurements. So this work has mostly been motivated by like some recent papers which claim that there can potentially be some bias from intrinsic alignments on even the boss measurements. Well, not bias, but they detected some effects at like 2.5 sigma level. Wait, cannot change the slide. Oh, okay. Okay, so just a brief introduction of what we are talking about. So the intrinsic alignments of galaxies are just the alignments of the galaxy shapes with the large scale density field or the tidal field. So the easiest way to visualize it is imagine that the galaxy shapes are aligned with the filaments, or that the elliptical shapes of galaxies are pointing towards clusters. So the intrinsic alignments are known to depend on galaxy properties. So mostly we have detected alignments for the LRG galaxies, and they tend to depend on the luminosity and the environment of galaxies, with like bigger, brighter galaxies showing stronger alignments. The second effect we have to think about is that the galaxies are ellipsoids. So we are talking about LRG, so they are ellipsoids, and then you basically pretty much randomly project them onto the 2D plane of the sky, and that's like the observed size of the galaxy that we see in projection. So depending on these like projection effects, the same galaxy can appear different like sizes depending on like what's the angle between its, let's say, major axis and our line of sight. So projections are typically assumed to be random, but once you have the alignments of the galaxy shapes with the density field, they are no longer random. And so now you have galaxy shapes that are aligned, and then you project them. And so these observed size of galaxies will then depend on the density field also. So the effect that is of interest is the alignments along the line of sight. We don't really care about how the galaxies are aligned in the plane of the sky for this like discussion. So what ends up happening is that if you look at the variations in the size of the galaxy, they will depend on some intrinsic alignment amplitude and on the matter field. And because what we are interested in is in the line of sight alignments, there is also this like mu square dependence here. And this is the kind of thing that will end up biasing that can end up that can show up in the like the clustering multipoles that we use for like RST measurements. So I will come back to this one again later when I talk about the RST effects. So another crucial piece is that we have this size dependence of the size on the density field, but we also need to have like a selection function that actually depends on the galaxy size. So once you combine these two, then suddenly the galaxy density field that you have observed, that the errors in your observed density field themselves depend on the density field now. So this effect is very similar to the fiber collision effect, where also like, if you have an overdensity, you're more likely to miss galaxies. Okay, so changing track for next few slides. So the way we'll estimate these variations in like the galaxy size using the fundamental plane. So fundamental plane is really an empirical relation between the galaxy size, velocity dispersion, and the surface brightness. You can predict this for ellipsoids using virial theorem also, but of course galaxies are more complicated, so there is considerable scatter and deviation from the virial theorem predictions. So in this paper we put out in 2015, we also observed that this fundamental plane does depend very strongly on redshift. So we also introduced some redshift dependent polynomial terms here to account for those redshift dependent effects. Once we have the fundamental plane, then we will define the size residual as just the observed galaxy size relative to the fundamental plane prediction. So in the literature, like these size residuals, like people have claimed you can use them to measure lensing because, you know, lensing changes the galaxy sizes. You can also measure galaxy velocities, densities, relativistic effects, anything that can, you know, like create deviations between the true galaxy size and the observed galaxy size. And we will use these also to estimate the biases in the RST measurements. However, so this is something we pointed out before also, and in this project we are going into more details, that fundamental plane also has a lot of systematic biases. So like I pointed out to the redshift evolution, so if you just take the standard fundamental plane and you measure its mean residual as a function of redshift, you see a very strong redshift dependence. This is a lossy sample, this is a CMAS sample. So we had to take about up to third order polynomials in redshift to account for most of this effect. And I won't go into this, but these fundamental plane residuals again depend on galaxy luminosities, colors. They also depend on your observational systematics like PSF flux, even the stellar density. Like I think Alexi also talked about this, that depending on the stellar density on the sky, your observed galaxy population changes. So that actually changes the fundamental plane also. So, okay, so now we already have a model for predicting how the size residuals that we are estimating using fundamental plane, how they will correlate with the density field. So we can actually go and test that model. So the way to do it is that we can measure the cross correlation function between the galaxies and these fundamental plane residuals. So this is really just measuring the correlation function where we have weighted one set of galaxies with this lambda, the size residuals. So these are our measurements for the blue is CMAS, the orange is lossy. There are some systematics on large scales in lossy, but we checked and we confirmed that it does not really change our conclusions by much. The amplitude can vary by like 10 to 20%. So yeah, so basic takeaway from this slide is that these size residuals are correlated with the density field. And because we assume, our model assumes that these correlations are actually caused by the intrinsic alignments, and we already have measured the intrinsic alignments in previous works, we just repeated that analysis. So we have the intrinsic alignments from galaxy ellipticities, and then we also have this fundamental plane amplitude from the cross correlations I showed in the last slide. And these are just splitting the galaxy samples by color. So going from red to blue, this is luminosity, going from brighter to fainter. We also look at satellite centers with galaxies, and open markers are the lossy sample, and then there are solid markers that are the CMAS sample. So you can clearly see that there's a trend between the intrinsic alignment amplitude and the fundamental plane amplitude. Part of this is expected if you think that, you know, both your intrinsic alignments and your sizes, they do depend on the galaxy properties and they kind of depend in the same way. So you do expect this trend. However, our model makes a very specific prediction that these two things should be equal. And that's just shown by this dashed black line, and data is not really consistent with that. So there's probably something else going on that, you know, there are some additional effects in these size residuals. So it's not just intrinsic alignments. The second prediction from the model is that, you know, there is this mu square dependence. So this is like the correct model. And so to test this, what we did was that we measured the multipoles now. So the monopole and the quadrupole. And instead of just setting it to -3, I just set it as like a free parameter and try to fit for it. So if this value was -3, this quadrupole should have been positive, but it's not. And if you fit for it, you see that there's almost no like this mu square dependence in these correlation functions. The only dependence here is actually coming from the galaxies themselves because the galaxies are in the redshift space. So this is kind of like strike 2 against the model that again, the data is not really consistent with what we expected. Okay, so that was like fundamental plane and testing if you can actually get these size residuals. For the next part of the talk, we are going to pretend that fundamental plane is still fine and you're still like looking for the effects on RST. So here's how the effect works. So we already established that these observed galaxy sizes are correlated with the density field. But to affect RST, you also need another ingredient that the selection function of your survey will depend on those sizes. So the way it works is that you can have some kind of a survey which, let's say, will ignore galaxies where you are observing, I don't know, higher surface brightness, or depending on how you like estimate the profile of galaxies. So you're throwing away some galaxies that are aligned in the plane of the sky, but you're observing everything that's aligned along the line of sight. So if you have some effect like this, then this mu square dependence will show up. So the way it works out is that your observed galaxy density will have some error term that depends on the size. And this error term can then be written in terms of this fundamental plane residuals. And we also have this response function in front, which depends on how your selection function will depend on how your selection function will respond to the intrinsic alignments. And we need this because most of your fundamental plane residuals are just random. I think I forgot to point out, but the RMS of like this, the lambda that we measured is like 15%, whereas the prediction, like what you expect from intrinsic alignment will be order of few percent or less. So most of it is random. So intrinsic alignments are really a small perturbation on your size residual. So you need like to measure this response function properly. So this is something that we are doing differently from what was done in the previous work, that they didn't really consider these effects. So once we can go and measure this gamma, assuming that the distribution of these size residuals is roughly symmetric and there are just small perturbations due to intrinsic alignments. And we estimated these and we have the full prediction of what the bias in RST should be for different samples. And then Byung-Gi went and also did the RST measurements for all of these samples and got these F sigma 8 constraints. So these are just showing you the deviations from between F sigma 8 and what our fiducial F sigma 8 was that we assumed using Planck cosmology. So I think this is CMAS, this is LOSI, and these are different subsamples. And green line is the model prediction, which is just saying that there should be like one-to-one relation between these two. And the data is clearly consistent with these null models, which says that there's basically no dependence in the growth rate measurements from size. So we can't really rule out the null model. And then in Martins et al., the main analysis they did was that they split the fundamental galaxy sample into two halves based on these fundamental plane values. So you have the negative lambda values and the positive lambda values, and you measure the differences in F between the two. In our paper, we have like 20 different definitions of fundamental plane for different reasons, but so we chose few of them that we trust. And we also got measurements from their papers, so thanks to Plisirata. So these points are using the fundamental plane definition from Martins et al., and the other ones are from our definition. So So again, our results are not really consistent with theirs, and this is primarily driven by different RST models used in the two studies. So for those, so Martin et al. Results are somewhere here and somewhere here for both Lozi and GMAS, but our results are like kind of all over the place. And this is actually consistent with our model because once you consider this response, we actually predicted almost like no detection, like no differences in F sigma across the two samples. So our model actually predicts something that's zero. Their model predicts something that's more like this red line. So that's just saying that the bias in F and differences in F and B measurement have some relation. And again, like these measurements are all consistent with the null result. I'm done. So to summarize, yeah, so we measured the FP fundamental plane, and we found that these fundamental plane residuals are very correlated with different galaxy properties, as well as many of the observational systematics. And once we did these cross correlation measurements and then compared them with the expectations from the intrinsic alignments model, the results are not really very consistent. And we also really don't have any significant evidence of biases in the RST measurements of BOS from intrinsic alignments. And for the future, I'm actually kind of excited for some cosmological applications of fundamental plane, but it does require further work before we can really use it for cosmology. Okay, that's all.
All right, we have time for a few questions.
Well, I think that for this year, we're working on to see this effect with the BTS sample, which is more sensitive to the effect. Because in addition to that, with the selection, we are using the morphology, so we may be sensitive to this intrinsic element of effect. So I think it was to study this effect first with the BTS sample.
So I think we haven't really done a detailed study for DESI, but you can definitely use our formalism to estimate like the biases in RST for like any samples. I don't know how much I would trust the results from fundamental plane yet. I think we need to study it a bit more carefully, but I think it can be done.
BGS is also fainter, so it should have less intrinsic alignment. More questions?
I know the size dependence of the selection function exactly. I can't just wait decide.
You can what?
Assuming no
So you can,
selection function weights for size.
if you know your selection function, you can, yeah, you can pretty much estimate this whole effect, right? Like the model predicts the whole thing. You don't have to use fundamental plane. You can use some other size estimator or whatever. But you can predict this effect exactly. Yes. Was that your question?
Any other questions? All right. If not, thank you. Suki again. All right. Next, we have Pat McDonald telling us about mock constraints on covariance matrices.
Okay, so I have a lot of words here, but the bottom, I wrote a bunch of words here, but the bottom line is, if you can calculate, if you're confident you can calculate a analytic covariance matrix, that's good enough, that's great. I'm assuming that you're not confident and you think you need to use mocks. And another thing to say is, I just want to know the answer to this problem. So if anyone has ideas they think are better, more promising than mine, please tell me. So the basic problem with limited mocks is that you have statistical errors in your covariance matrix estimate. And I like to think of this as you have small eigenvalues, accidentally small eigenvalues in the covariance, which cause problems when you invert the covariance matrix to compute chi-square. You overweight these modes of variation with the small eigenvalues. The scale of the problem, the number of required mocks, is set by the number of data points, because if you have less mocks than data points, you're guaranteed to have 0 eigenvalues, and the chi-squared will blow up. So I wanted to be able to quantify this problem and test solutions. So I invented a very simple test scenario where I typically use 128 data points. The baseline errors are diagonal with some dependence on the data point index, just so there's not artificial symmetry. The theory is just fitting the mean of these data points. I normalize the errors to make the true error 0.01, and I generate lots of realizations to test the statistics of your analysis results, like of order 100,000 realizations of the whole thing typically. So this is the lowest order problem. This is an example with 192 mocks. Remember, 128 data points. The black line here, traced also by the green points, is what you would get for the mean of chi-squared as a function of the theory parameter averaged over many realizations. The red line is what you get if you just use the raw covariance matrix estimated case by case from the mocks. And you can see your errors would be much too small. The simplest sort of solution to this is what's called a Hartlap factor, where you can compute just one overall number to rescale your mock covariance matrix by, which depends on the number of mocks and the number of data points. And here, that factor is a factor of 3. And using that gives you these green dots for the mean chi-squared. So you can see it works perfectly in the mean by design. But that doesn't necessarily mean that it'll work case by case. So these green dotted lines are 20 different cases. You see, like, one of them rules out the truth at almost 4 sigma. So I wanted to quantify that issue or potential issue more clearly. So there's lots of, I settled on testing how often the truth is ruled out at 3 sigma relative to how much it should be if you had the correct covariance. And that's what this plot is. So it's as a function of the number of mocks. I show if you use the raw covariance as the red line and the Hartlap factor as the black line. So the bottom line is if you had 5 times as many mocks and thought, I'll just use the Hartlap factor and I'll be okay, it's not really true. You'll rule out the truth a lot more often than you should. So what can we do about this? And my answer to most problems is we'll write down the full likelihood and marginalize over uncertainty, in this case, uncertainty in the covariance matrix. And I'm kind of mocking myself because this doesn't work very well in this case, but at least the first version of it. So, but let's go on. So you can, for the data set and each mock, you have basically a copy of the Gaussian likelihood function. So the constraint of O is the data set and M is all the mocks. This is the constraint on the theory parameters, which are theta, and F is just defined as the inverse of the covariance matrix, and mu is the mean of the mocks. So you have the data part, and then you have the mock part. And you don't care about the mean of the mocks or the covariance intrinsically. You just want to know the constraint on the theory parameters that comes from the data set and the mock set. So you want to marginalize out the covariance and the mean of the mocks. You can do the mean of the mocks analytically and get to this sort of master equation, which has the data term and the mock term with the raw covariance matrix of the mocks sort of constraining your covariance, true covariance that you want to marginalize over. So the first thing I thought is, well, if you can, you'd like to marginalize over all elements of the covariance matrix. And this has actually been done in a recent paper by Hall and Taylor, where they use this prior, which contains an analytic estimate of the covariance, and then that's the C0, and then a parameter N, which quantifies the strength of the prior, basically in terms of like how many Machs you would measure this covariance from. So when N goes to infinity, this is like a delta function where the F inverse is fixed to C0. But then as N is not infinity, it allows, deviations from C0. Hall and Taylor required this N greater than the number of data points to make this prior normalizable, but that doesn't seem necessary because, well, priors don't have to be normalizable. A flat prior isn't normalizable, and you're generally happy with that. So if you allow N to be less than, go all the way to 0, then you can see that C0 doesn't matter anymore, and this becomes the uninformative prior of another paper by Salentin and Heavens. So this paper, Salentin and Heavens and Hall and Taylor, are connected by the value of N. So you do this analytic integration and get this beautiful formula, which gives you your constraint on theory parameters from some data set in Machs. This chi-squared involves a C covariance matrix, which is just the weighted average of the Mach covariance and this prior analytic covariance. And the functional form really looks different than Gaussian, but it isn't really for large values of the data points in Machs that we're typically would be talking about. Unfortunately, this just doesn't seem to work in practice. So this is the rate of ruling out the truth over ideal as a function of the number of Machs again. And the first thing you notice is, so the top includes the Hartlap version and also the N equals 0, which is the Salentin and Heavens, and they're practically the same. So actually Salentin and Heavens for this number of data points and things and is just another way of producing Hartlap. But even as you make if you make the constraint stronger, so fixing the covariance to this prior, you still rule out the truth more than you should. And my thinking is that if you marginalize over the uncertainty in the covariance, even if the sort of best fit value can be, eigenvalues can be small, a small number of Machs won't rule out having bigger eigenvalues, and that would be accounted for with the marginalization, but it just doesn't seem to work. It does, you're okay, you don't rule out the truth too much as N becomes large, but that's just fixing to the prior, which is in this case the truth. So I set up another case where I add a random constant to all the data vectors and Mach vectors so that the prior is not correct. And then the results with a strong prior are worse than the results with a weak prior. And basically, this method just doesn't work. So we need to try something else. And my thinking was that it seems like the only mode of variance that really should matter is ones that look like changes in the theory. So there's a lot of changes that in the data set that must not matter. So I thought, let's use the theory itself to tell you what modes to fit for from the Machs in the covariance. So this is my model for the covariance matrix, which is the analytic covariance matrix, which would have been the prior before, plus some parameter constant times the thing that makes, these are derivatives of the theory with respect to the theory parameters. This makes a term that looks like a change in the theory parameter in the covariance matrix. And you can use the same likelihood function as before, to fit for or marginalize over this parameter of the covariance matrix. And this seems to work beautifully in my tests. So first I have the a case where I'm like before, I have C0, which is diagonal, but I've added a constant, random constant to all the mocks and data, so C0 is not exactly correct. I have two different ways of estimating this parameter of the covariance. One is the red line, which comes from, this is the rate of ruling out the truth of 3 sigma again, comes from just fitting this parameter once and for all to all the mocks and using that to fit for the theory. And this works great, where notice that the scale, I've changed the scale of the number of mocks here. Before, most of the plot was a greater number of mocks than data points. Now it just works perfectly for more mocks than data points. And what I'm interested in is how few mocks can you get away with? So it works well for just fitting to the mocks once and for all, but a closer thing to really marginalizing over this extra parameter of the covariance matrix is to maximize with respect to it for each theory parameter value. That's the black line. And that works great for it doesn't rule out the truth too much for any number of mocks, even as you get to 0. Of course, something must go wrong as you go to 0 mocks, and that's shown by this blue dotted line, which is not the rate of ruling out the truth, it's the width of the likelihood function at 3 sigma. So as you go to 0 mocks, your errors are getting bigger. The likelihood function is getting wider because you're having to marginalize over this uncertainty in the covariance matrix. But you don't have the problem the really bad problem of ruling out the truth too much. So if you're paying careful attention, you may notice that the flaw, the wrongness in my prior covariance matrix there was exactly the same as the model I am fitting for it. So maybe it's not too surprising that that works well. What's interesting is, does this work when your covariance is not wrong in that way, in this way that's consistent with the variation of the theory parameter? So here I make a harder test, which I have the prior covariance is just half the true covariance, which is a disaster if you ignore it, but looks nothing like this constant theory variation term. And this works great too, where ruling out the truth a little more than you should, that's fine, in my opinion, as long as it's not just by making the error bars wider, but as long as you're constraining, you're basically constraining things well, which is what's shown by the blue and green curves. That's fine to rule out the truth a little less than you should. And I have another test where I just have another functional form of this contaminant, this deviation from the prior covariance. It works, but again, not the same as the one I'm fitting for. It works again very well. So what I kind of hoped for, but wouldn't have been too surprised if it hadn't worked, seems to be taking place, that as long as you fit for the mode of variance that you most care about, which is one that looks like the theory parameters, it seems like you get good results. So the prescription, the recipe for using this would be when you're writing the paper where you report some data point measurement, you include both your best analytic covariance estimate and your raw mock covariance. And then the user could, depending on their theory, jointly fit these as part of their parameter fitting. So it seems promising, but there's a few loose ends here. One of which is I only had one theory parameter. And if you have more theory parameters, you're going to get more parameters of this covariance matrix. I don't think this is too big of a problem. In the typical case we'd be talking about where you have the problem because you have many, many data points. Your theory parameters, you don't have nearly as many theory parameters as you have data points. You just deal with it. Another potential issue is this should work well when your theory parameters are very tightly constrained. So these derivatives really describe all of the relevant variation in the data, predictions allowed by the theory. If the parameters are not so well constrained, there may be, and they're nonlinear, there's modes of variation that will be not included in there. You can think of ways of adding some modes, but that needs to be tested. And finally, I'd be dishonest to not say that very preliminary tests with Florian on BOSS data aren't quite working perfectly. And I don't understand. I suspect this is not fundamental and we can figure it out, but I have to say it. So the bottom line conclusion, I mean, the really clear conclusion is you're not safe using a heart lap factor. And these other published modes of marginalizations over the full covariance, they look beautiful, but they don't seem to be safe using them either. And then I have my idea, which if anyone thinks they have better ideas, I'm happy to hear them. Or that also maybe looking for this kind of general solution is just not a good idea, and you should always just think about the problem at hand and try and figure out sort of ad hoc solutions.
So if you're going to make use of the theory derivatives, you also just do a data compression.
Yes. And I have a what would you call it, aesthetic preference for, sort of forward modeling where you don't mess with the data points, you try to fit them. You'd have to come up with that. If you leave the data intact, you can still do a full nonlinear fit to it. And if you're, you haven't lost anything. Yeah, it certainly is. It's my motivation, thinking, I know I can do that. So what can I do in the forward direction was my motivation for this term that I added. It's sort of trying to turn that around and go forward with it. Yeah.
Right.
So in the context of this super sample variance and stuff like that, we've done similar things. And the lesson there is that the last point that matters most, because the errors highest k in some sense, because that's the most error. So you don't have a whole vector at all, you just have 1 point essentially. And you need to just get the variance on that last point right in the sense of how much, for example, super sample variance contributes to that last point, and how that is degenerated on the parameters, right? So the idea was similar, right? You try to decouple the scale variance, but in practice it didn't work that well because the errors are changing so rapidly with scale.
I don't know what that means.
It means you don't have a whole vector. You think you have a vector, right? And I'm saying, well, it's just 1 point that will give you your accuracy of the cosmological parameter.
Using the best constraint.
Yes,
yeah.
Right. The point where the error is the smallest. So,
That's
take k of 0.2 or 0.3 for z, right? And you basically need to estimate what, for example, the contribution of the super sample variance is to that point. In the presence of all the sampling variance, in other words, in the presence of all the disconnected parts. That's why this is hard. I'm trying to say your toy model and doesn't necessarily apply to the project. Okay.
I'm not sure it does as little as you think. I mean, I purposely have my RMS errors are 1 over the index. So they do, you know, start large and become small at the end. And I have a constant, so that constant is more important at the high K, at the high index end. And I have something that you're not doing, which, or weren't necessarily doing, which is I can fit for this thing over as I vary my theory parameter. It's just not clear to me that what you're saying you did is as similar to what I'm doing as sort of you think it is.
It certainly was written in that form, right? I mean,
Did
No, we better move on. I think we're getting it.
okay.
All right, thanks. Let's say thank Pat again. All right, next we have Jay Wadaker telling us about analytic covariance matrices for the galaxy power spectrum.
Hi, I'm Jay Wadekar. I'm a PhD student at NYU. I'm in my 5th year, and I work with Roman Skochimaro. And so I thank the organizers for giving me an opportunity to present these results. So we were working on an analytic covariance of the redshift space galaxy power spectrum. So I'll present some of the results and the insights that we gained from the project. So actually, I thank Pat for motivating some part of my talk that there are some drawbacks of using mock simulations because we need like a large number of mock simulations to estimate the covariance. So I've just like made a brief slide about how you estimate this covariance from mock catalogs. What you do is you have, sorry, some text is gone, but you basically simulate like thousands of dark matter boxes which have sizes of like around gigaparsecs, and then what you do is you paint first you paint halos on them, then you paint galaxies on them, and then you cut your survey volume, and from each of these realizations you calculate the power spectrum, and then when you combine all these power spectra, then that's what gives you these red error bars on the power spectrum, and this is how you calculate errors from mock simulation, and you get these black dots from data, you have these errors from all these thousands of mock simulations, and then you get constraints on your cosmological parameters. So one thing to emphasize is that you have to use like approximate simulations for dark matter, because you cannot use full n-body simulations until you are like, okay, if you are funded by some billionaire like Jim Simons, maybe you can, but otherwise we have to rely on these approximate methods. So, okay, what's like drawback in this traditional approach? It's that as the survey volume increases, I have to simulate bigger boxes because I have to fit my survey in that bigger box. So these mock catalogs, they become tougher to simulate as we go into like upcoming and future surveys. So this is going to be a drawback for the traditional method. The second drawback of this all these traditional methods is that the covariance, the dependence of the covariance matrix on cosmology and bias is computationally prohibitive, because if you you do all the process that I showed in my previous slide for one set of cosmology and bias parameters, and so if you look at the power spectrum likelihood, what you should would be doing is that you should also like consider the dependence of covariance matrix on cosmology and bias parameters. But what you do is you throw it under the rug and you ignore it, because you cannot do the whole mock process for a different cosmology or bias. And then the last point which Pat also emphasized was that the mocks, they suffer from sampling noise, and in some cases like there might be like some spurious elements in your covariance which can make it harder to invert. So okay, so I know that I'm going to run out of time till the end of my talk, so I'm just going to show my results before. So this is like the comparison for our analytic method to patchy mocks. So these patchy mocks were kind of the state of the art and were used for the SDSS BOSS parameter estimation. So the results that I'm showing are for diagonal autocovariance. And as you see, like our method like works to all the k values that we checked, even till like very like end of the quasi nonlinear scales, k equal to 0.6. One thing to emphasize is that this is not a fit to the mocks. So what we used was that we only used the linear power spectrum and the linear bias from patchy. So this is like entirely made from first principles, and it works pretty well. And actually, one another thing to emphasize is that like this analytic method, it takes like less than a minute to calculate. But then when you see these mock simulations to like calculate all these 2000 mocks and the covariance, it needs like around months. So to give you an estimate, like the Apache mocks were made, I mean, it took the collaboration around like 5 to 6 months to make the final version of the Apache mocks. So I mean, this is an advantage of the analytic method, that it takes like much lesser time than the Apache mocks. So the last slide was only about diagonal elements of the autocovariance, so monopole cross monopole, quadrupole cross quadrupole. But then I'll show you all the 4 cases. So the diagonal, off diagonal elements for auto and cross covariance. So here in this slide, I've shown off diagonal elements of the auto covariance. So I've shown like 2 rows in this figure, 2 rows of the covariance matrix. So the one of the rows in the covariance from Patchy is given by the blue line, another row is given by the orange line, and the analytic results corresponding to the blue line for that row is given in the red dashed, and the analytic results similarly for the orange is given in the black dash. And as you see, I mean, even for the off diagonal elements, the analytic method works pretty well. And okay, so then I will show these are the results for the cross covariances. So we did the we could do the analysis for all the galaxy multipoles, power spectrum multipoles. So these are the diagonals shown on the left, which also like agree pretty well with the analytic covariance. And on the right, I've shown the off diagonal elements of the cross covariance, so monopole cross quadrupole or monopole cross hexadecapole. And as you see, like so in these plots, it's evident that this, even when you have 2000 mocks as the patchy simulation, like this patchy covariance has, even then you have a high sampling noise, and you can have like some spurious elements in your covariance. And the analytic method does not have any noise, so that's one more advantage. And then, I mean, as you see, I mean, like the cases I've shown, they work very well. But then there are like some of the cases, like here, I mean, at high gain, we are finding like slight mismatch. But then we know why this mismatch is going. Like there is this slight deviation, but we know, I mean, what prescriptions we have put in and what we need to put in to get this even better. So okay, I mean, let me now like talk about the effects that we have put in, and then I'll go into like some insights that we gained from this analysis. So the included effects that we have to use to model this covariance is that first we have to use the highly non-trivial survey mask. So the survey is like non-trivial along the line of sight because we have the radial selection function, and even in the angular case, we only see like a part of the sky. So you also have a non-trivial angular part, and we have to model that in your analytic calculations. And then we need to use short noise. We use the Poisson approximation for short noise, and then we also used redshift space distortions. We used like the Kaiser approximations. Did not use fingers of God. I'll come back to this. Then we have the linear, non-linear, and non-local bias in our calculations. We also have, we use the tree-level trispectrum. So the 4-point function, the covariance of the power is essentially the 4-point function. So we can also calculate the tree-level trispectrum. We did not use loops. I'll again come back to that. And then an important effect for modeling the off-diagonal elements is there is this mode coupling between long wavelength modes, like almost of the order of survey size or more, coupling to these small modes, which is called the beat coupling effect, or later called the super sample covariance. Okay. One thing I forgot to mention, actually, sorry, was that this effect of this highly non-trivial survey mask on the covariance was also done by the Berkeley group, and we have used like the approach was very similar to what we have used for the mask. Okay, so then I mean, let me get to the crux of the talk. Like, why is the analytic method working to such like non-linear scales like k equal to 0.6 that we check, even though we do not include loops or fingers of God. So so I've shown like the plot for this quadruple cross quadruple diagonal elements, and if you see like power spectrum quadruple and try to model it using your analytic theory, if you do not include fingers of God, you already have a 100% error, I think, at like 0.2. But then we do not include fingers of God in our analysis, and we still find like almost perfect agreement till k equal to 0.6. So the answer why this analytic method works is that I think we saw that like a short noise was the effect that was dominating at high k. So like I've shown like the breakdown of the covariance into this various effects on the plot on the right. So the plot on the top shows the diagonal elements of the monopole cross monopole covariance, and the plot on the bottom panel shows the row of covariance matrix. This row is at the diagonal element of the row is like equal to 0.22. So then if you see on the top plot, so you have your short noise in the Gaussian part is given by the red dashed line, and the short noise in the non-Gaussian part is given by your green dashed line. And as you see, I mean, once I go beyond k equal to 0.1, the dashed lines like take over the solid lines. The black is the total of all the effects put together, the final covariance. So if you see, the final covariance is like almost at high k, it's almost completely dominated by short noise. And short noise is what we can model using our analytic calculations pretty well. Because I mean, if it was the case that there was this non-Gaussian parts which were dominating at high k's, then we would not be able to model the covariance, because we do not use loops in our analysis. But then, as we see, I mean, the short noise washes out entirely the other contributions. So even if we get these lines a bit wrong, we are still doing pretty good in predicting the final covariance. Okay, also not just the diagonals, also the off-diagonal elements at high k's for the monopole cross monopole covariance. It's also kind of like dominated by short noise, which is dashed line. So this short noise is the short noise in the non-Gaussian part. Okay, so then this effect is not just for monopole; it also like contributes for quadrupole. So the quadrupole power is, I mean, the design says that there's no short noise, but then in the covariance you still get short noise even in the quadrupole covariance. So that's what we see. So these are the diagonals for the quadrupole cross quadrupole quadrupole cross quadrupole covariance, and you see the diagonals of these are also very heavily dominated by short noise until high k. So that is why the analytic method is doing pretty well. And then, okay, one more effect that you have to consider now in this bottom plot I've shown for a row of the covariance matrix. You can see like the off diagonal elements, they are the short noise is the green dashed line, and there is this non-Gaussian part which is contributing to the off diagonal elements. But then this non-Gaussian part is made up of like two components. The first component is this tri-spectrum, the 4-point function, and the second component is the super sample modes contributing to your covariance. And then we also found that this off-diagonal part for quadruple is dominated by super sample covariance. And the good thing about analytic method is it models super sample covariance pretty well, because these super sample modes are on much larger scales and can be very well modeled using analytic theory. So it works even for this quadruple cross quadruple case. Okay, so then I mean all these plots, I'm emphasizing that this short noise is what is making this analytic theory work. So all these previous plots were made for the Boss analysis. So exactly the survey window that Boss used, exactly the number density that Boss had in their analysis. The number density of galaxies is the same that Boss had in their analysis. But then would this method work for future surveys? So this plot actually shows the signal to noise for the upcoming and some future surveys. And the redshift surveys are typically designed such that your signal to noise is a factor of few at the BAO scale. So this is the signal to noise for Boss is shown in this red line. and which is what I've shown the results for. But then you can see that. So let's see Euclid, for example. The Euclid is given in this blue line. So the signal to noise is kind of like similar to what Boss had in their analysis. So our method, as we showed, like the short noise being like 10 times more than other components, that would hold even for Euclid. And then I think this method looks promising for Euclid. So for DESI, DESI is shown in this black line, and a lot of the high redshift samples or even the LRG samples, I think, can be modeled pretty well using this analysis. Because the signal to noise is comparable to BOS. But then you have the BGS galaxies, which are like a factor of few higher in your signal to noise. But then, but if you see my previous plots, like the short noise was a factor of around more than 10 higher than the other effects. So even when you include like this increase in signal to noise, I think it would still be dominated by short noise, and we would still have like a good comparison from the analytic calculation. Okay. Okay. So I'll talk in brief about like other effects that or these insights that we gained from this calculation. So one important thing is that I get this question, which is that do you need to model like your non-Gaussian covariance? So for the non-Gaussian covariance, you have to model the super sample effect and this trispectrum, and then is that important? And it's almost always neglected in forecasts that you see for spectroscopic surveys. And then so when I make the signal to noise plot for the parameters that were used in BOS, we are finding that actually if you use the Gaussian covariance, you will over predict the amount of information that you have in your survey. And actually, the non-Gaussian part causes like almost like 40% of leakage of information for if you use k max equal to 0.3 in your analysis. So I mean, you should when you make forecasts, I think you should be modeling both the Gaussian and the non-Gaussian components. Right. Yeah. Yeah, even in the non-Gaussian component, the short noise dominates. I'm talking about the entire non-Gaussian component. So for the quadruple, it's not the short noise which dominates in the non-Gaussian component. But if you only include Gaussian covariance matrices in your Fisher analysis, for, let's say, then you would over-predict the amount of information. You should include the non-Gaussian part in your analysis. Yeah. Yes. So what you do is usually you model the diagonal parts using the Gaussian. The diagonal part is mostly dominated by linear theory. So that's what I mean. If you only include what you see in Fisher forecast, is that you only include diagonal covariance with some effective survey volume, and then you would over predict the amount of information. It is. Okay, but then yeah, there is this also goes back to like this the question on day one that Subdeep had written down, that should we go beyond the power spectrum? So I mean, if you are like pushing your analysis to high K, it does seem like you are losing like a lot of information to these. Lot of information is getting leaked from your Gaussian case to the other statistics. Which you should, I mean, try to recover by doing bispectrum analysis or trying to recover this information from super sample modes. And we should like try to think more about how you can like recover so much information that is being lost if you push your analysis to high K. Okay. So one thing I want to emphasize was that this loss of information, we saw that. So in this plot, like 40% of information among this 40% of leakage, I think like we saw that 20% was due to these super sample modes. Even in the quadruple, the super sample modes are what is like causing this leakage. And so, this was like a slide like just showing what I mean when I say the super sample mode. So what I mean is basically if this is your, let's say your BOS survey, there could be like modes which are like larger than your entire survey, and these might like cause variation in small scale fluctuations in your survey. So when you have a survey present at the over density, you will get your small scale fluctuations to be enhanced. As this behaves like a universe with positive curvature, or if you want to understand it other way, it's like a high omega matter universe. So Ian has worked a lot on these effects, and then so these effects, I mean, should be considered, because I think like these super sample effects are what is causing like this leakage of information for even for the monopole and the quadrupole. And so actually what we in our analysis, when we did our analysis, what we found was that this effect of these long modes were these super sample modes were like almost 5 times stronger than what people had previously considered for spectroscopic surveys. And so I mean, I won't go into the details for why we found like this. We can talk later because I don't have time. But then I just wanted to emphasize in the end that people should also try to think about like these super sample modes, and because they cause like a lot of leakage of information. Okay. I'm out of time. Okay. But okay, so let me just give summarize my talk. From our results, we think that analytic method is an excellent alternative to MOX for redshift space covariance, because we see that short noise and these long modes, they dominate at high K. And both of these effects, short noise and long modes, are very well modeled using the analytic theory. And we see that this dominates over the non-linearity. So these mocks, I mean, we use these mocks because we think like these non-linear effects that these mocks simulate are important, but it seems like it's all washed by short noise and these long modes. So and both Gaussian and non-Gaussian parts of the covariance matrix are important. And then so it would be good if we can use an analytic method to make the bispectrum covariance, because right now, I mean, we have like around 2000 passive mocks, and if you do the bispectrum analysis properly, you have around like 6000 triangles. So to find errors on all those parameters, I think mocks are not sufficient. So and this was like the bottleneck that was there in the BOSS bispectrum analysis. So if we can model the bispectrum covariance using analytic theory, it would be I think a pretty good yeah. Okay, thanks. I mean, so we okay. So I mean, what we did was we used the binning k equal to like 0.05, and I think, I mean, the binning, what binning does is sometimes it like smears out the Gaussian part like, but I don't think I mean, we can use the analytic method for both cases. The binning does not matter. So in the end. Mm-hmm. Yes. 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 It is still robust when you do this thing. Yeah. We have to recalculate some of the window kernels, but then we can do that. Yes, and the analytic method would work. Yes. Okay, Martin.
It's a little worrying that the level of agreement with elements of the covariance matrix is because of this large short noise, right? Because that's a very low rank mode in the matrix. There's a lot of other modes, therefore, you're getting wrong. So even though element by element they look good, the actual finding value structures. It's a little bit like in the power spectrum. If I go to very high K, it's dominated by short noise. That doesn't mean I can't use high K to get any information at all, because the short noise is a constant I subtracted, and I can still, the error bars are small, I can still make a fantastic measurement. But a few days ago, right, going to the nonlinear regime, working all the way to K of 1 is going to revolutionize the world. It's entirely short noise scales. So if I just plotted the elements of the power spectrum in each chart, it looked like my model was fantastic.
Yeah, but for the covariance, I mean, to get the elements right, I think like, do you think there are some eigenvalues which we get wrong?
Well, you know, the shot noise has got some very small number of degrees of freedom.
Yes.
So there's some additional, you know, V times V transpose, plus V2 times V transpose, etc. added.
Okay.
There's a small number of terms.
Okay.
So the real question is how, you know.
No, but Martin shot noise is diagonal. It's not low rank. It's the opposite. Right?
It's got window functions.
Right? That he's handling them. Right?
Right, but in the matrix, it's. So.
But I think like if we see, I mean, we did the signal to noise, but we didn't do the parameter constraint. But if we find any difference, I don't think I mean, if you compare this analytic covariance versus the patchy and if you find parameter constraints being different, maybe then, but otherwise, I mean, if they're not different, then I think then it doesn't matter. You can use an analytic. But I mean, even if you think like the non-linearities affect your covariance, then even these approximate methods that you use to do mocks, those are not good at the non-linear scale. So, yeah. I mean, what we are just showing is that these mocks, I mean, what they are doing mostly is like at high phase, you are just getting short noise. That's what it is working.
So we can split the connected part into super sample part and whatever is inside of the survey volume.
Yeah.
And I mean, have you done which one is more important on the cosmologic parameters in the end, on F sigma and for that?
No, actually, we were actually like planning to do that, but we are like still a bit delayed in that analysis.
If you kind of make the argument that super sample is more important, we find that that's not true. Still,
at least for the information content, that was the argument. Just looking at the information content.
Yeah, that doesn't propagate necessarily the error on ground.
Yes, that should be. I mean, yeah, we are working on checking this on parameter. Yeah, it should be.
Okay. Let's thank Jay again if there are no more questions.